All right, 12.4 addition and complement rules. All right, so we're looking at first mutually exclusive events. What does it mean for two events to be mutually exclusive? That means there are events that cannot occur at the same time, or in other words, events that do not have anything in common. So in other words, if you're talking about flipping a coin and rolling a die, flipping a coin and rolling a die, they don't have any outcome in common. So they would be considered mutually exclusive events. Mhm. All right. So the way we would calculate the probability of mutually exclusive events, looking at the probability of event A or B occurring, we would just find the probability of each one of them individually and add them together. All right, so we're okay. So next we're gonna, before we actually get into an example, we're gonna look at the standard 52 card deck. All right. So just in case you haven't dealt with cards before, haven't dealt with cards in a long time, you have four suits. That'll be clubs, spades, hearts, and diamonds. Two black suits. That'll be clubs and spades. Two red suits, hearts and diamonds. Got 12 cards, not 12, 13 cards each suit. So there's 10 regular cards and three face cards. Three face cards are going to be king, queen, and jack. Then your 10 regular cards would be your ace. And then the 2 through 10, the numbers 2 through 10. All right. All right. First example, suppose a single card is drawn from a standard 52 card deck. Standard deck of playing cards. Find the probability of drawing a 5 or a king. I'll let you write that down before we get into it. All right. So the first thing we want to ask is what I have in the red. Are the events mutually exclusive? And the answer is yes. Let me write that a little better. They are mutually exclusive because they have no cards in common. All right. So in other words, there's no such thing as a king of fives or a five of kings. So it's either a five or it's a king. They have no cards in common. All right, so let's look at one at a time. Looking at the event drawing a 5. And that one could be better. Probability of drawing a 5. Now, our sample space, the number of cards that we have is 52. And this is an actual 5, not an S. So the number of 5 that are in the deck is 4. So the probability is going to be 4 with 52. I always say reserves. We could reduce this fraction, but I always suggest reducing it after you add your fractions together. So we'll reduce it before the end of the thing, before the end of the problem. So now looking at drawing a king. Once again, there are 52 cards in the deck. There are 4 kings in the deck, so we do 4 over 52. That's the probability. All right, questions on either one of those? Your sample space is always the total number of cards you have to choose from. Then your event is how many of whatever cards you're dealing with or want to find. So from there, if you wanted to find the probability of a 5 or a king, drawing a 5 or a king, you take both of those probabilities, add them together. So that's 4 over 52 plus 4 over 52. That'll be 8 over 52. Then reduce to 2 over 13. All right, any problems with that? All right, let's scroll up. All right, so the general addition rule, probability of A or B occurring, is very similar to what we just did. Take the probability of A plus the probability of B, but then we have to minus what they have in common, the probability of A and B. So remember before, if they're mutually exclusive events, they did not have anything in common. But if they do have something in common, we do have to subtract that probability, and you'll see why in a second. So if they're mutually exclusive events, this is not a big deal, that because that's 0. They don't have anything in common. But your general addition rule, we do have to consider this, and you'll see why in a second.
Wait, I'm sorry. So you saying they're not mutually exclusive, but we have to consider a mutually exclusive rule?
For probabilities for events that are not mutually exclusive, we have to do your general addition rule, because that means they have something in common, which is this piece right here. Now remember, this was for mutually exclusive events. Where it go? This right here. So that means they don't have anything in common. So that piece right here would be 0, right? If they don't have anything in common. So that's why they don't consider it here. If it's mutually exclusive, then all you have to do is just add their probabilities together. But if they do have something in common, then we have to consider what they have in common. And so, like I said, you'll see why in the next example, we have to look at this part right here.
All right, facts. Thank you.
Yep, not a problem, not a problem. All right, so let's look at, let me erase this real quick. So a single dice roll, find the probability of rolling an even number or a number greater than 2. All right. So a single dice roll, we're going to find the probability of rolling an even number or a number greater than 2. So if we look at these two events that we have, We have an even number and a number greater than 2. So this is the first one right here, wrote in an even number. Remember we talked about a single die before? A single die, the probability, not a probability, the sample space is 6. We have the numbers 1 through 6 as our options. So that's why that is 6. So if you're talking about the even numbers, in that sample space is just 2, 4, and 6. All right. And then that means we only have 3 numbers that are in that event. And so we place the 3 over 6. And that's the probability of getting an even number. It's 3 over 6. Take the number of your event, number of outcomes in your event, place it over the number of outcomes in your sample space. Same thing we did with the cards. Now, if you're talking about our second event, number greater than 2, once again, our sample space is still 6. And our numbers that are greater than 2, 3, 4, 5, 6. So we have 4 of those numbers. And we'll do 4 over 6 as that probability. So before we go any further, is everybody okay with that? Make sure we're okay.
This is a small question, but
Mm-hmm.
the letters that you're using, is there like a specific place you're getting them from?
No, you can use whatever you want. I did E for even and G for greater.
Gotcha.
But yep, you can just use whatever letters you want to just make a difference between your events. Yep,
Okay, thank you.
not a problem. Good question. Good question. All right, is everybody good before we keep going? So I just wrote this note right here in red. These events are not mutually exclusive. And so what I mean by that is that they have outcomes in common. So that means it is possible to be even and greater than 2. All right. So we notice that 4 and 6 fit that description. All right, being even and greater than 2. So now the reason why we have to look at that is because if I look at my probability of 3 over 6 and 4 over 6, if I were to add them together, I get 7 over 6, and which will give me something greater than 1. So I know something has to be wrong with my probability. Remember, our probabilities cannot be greater than 1. But if we look at what we have here, we have 4 and 6 here and 4 and 6 here. Both of those probabilities will count 4 and 6. So that means when we add those probabilities together, we're actually counting 4 and 6 twice. So that's why when we go here to our formula, we have to subtract one of them. So whenever you're adding or whenever you're trying to find a probability of two events that are not mutually exclusive, in other words, they have something in common, we have to subtract what they have in common once from them, because if not, you're counting them twice. Once again, we counted 4 and 6 twice if we were to add those probabilities together.
I got a little lost. I'm sorry.
Nope.
Just within the words.
Okay.
So you're saying that when we're counting the 4 and 6 for the probability, you said, what about us? What are we doing with the 4 and the 6 twice?
Okay. When you add your probabilities, remember your formula to find the probability is to add your probabilities together.
Facts. Yeah.
So now when I add them together, though, I'm going to count 4 and 6 4 and 6 is a part of this probability, but 4 and 6 is also a part of this probability.
Okay.
So when I add those together, I'm going to actually be counting 4 and 6 twice, because 4 and 6 is a part of both of these probabilities.
Yeah. So why you ain't write it down?
Well, they're
It says,
included. When you say I didn't write it down, what you mean?
because you said you're also going to be including the 4 and 6 twice because it showed up in both places. Are you just like speaking? I thought it was something that was included within the problem, though.
Right. So in this 3 is 4 and 6, right?
Yes.
And then in this 4 is 4 and 6.
Mm-hmm.
So that's why when we go here, we have to subtract it. You see what I mean? Like we don't want to count 4 and 6 twice in our calculation and our probability. So that's why we subtract it right here in the formula.
Okay.
So right here, you know, notice I said that we have to calculate, okay, what's the probability of getting 4 and 6?
Yeah.
And that's, you know, so that's why we have to subtract it here. So we're not counting it twice. We don't want to count it twice.
Facts. Okay.
Yeah.
Okay, I get what you're saying.
Okay.
Thank you. My bad.
No, you're fine. I want to make sure you understand it. And you asking the question helps other people to get that repetition of what was said as well. So no, you're fine. So problems with that. So that's why, you know, we have this extra step right here. We find the probability of being even and greater than 2. Once you find that, then you plug all your 3 pieces into the formula. And we do 3 over 6 plus 4 over 6 minus 2 over 6. And that'll ultimately give us 5 over 6.
Another really quick question. So the E and G equals like the 4 and the 6. The N, E, and G, that's just counting how many numbers are in common?
Yes.
Okay.
Yes. Yeah, you're talking about right here.
Yes.
Yep. So in other words, we had 4 and 6. It was only 2 numbers that were in
Got
common. And that's the number you use in your probability.
Gotcha. Okay.
All right. Questions on that before we do another example? All right. Let's scroll up. Everybody good? Oh, let me see what this one is. Yep, same type of situation. All right. So in the table, the data shows the results of an experiment conducted to test the effectiveness of a flu vaccine. If one person is selected from this population, what is the probability that the person was vaccinated or contracted the flu? Give you a chance to write that down. All right, scrolling up to see the chart. So V, oh, wrong button. V just represents vaccine, F represents flu. So vaccine, no vaccine, flu, no flu. You know, 21 represents people who had the vaccine but still caught the flu. 198 got the vaccine and didn't catch the flu. 219 is all the people in total who got the vaccine. So this is no vaccine but caught the flu. No vaccine, no flu. And then 271 people who didn't get the vaccine at all. So that's how we're reading that chart. 97 people contracted the flu. 393 didn't. So 490 people altogether. All right, scroll up. Okay, so our sample space, kind of already mentioned that already. It's going to be 490. That's the total number of people altogether. All right. So we want to know, going back to what they asked, what is the probability that the person was vaccinated or contracted the flu? So that's what we're looking at right here. Probability of vaccination or flu. So going according to our formula, we want to look at the probability of you were vaccinated, probability you caught the flu. Then we're going to subtract the probability of being vaccinated and had the flu. Our bottom number in each one of them is going to be 490. Remember, that's our sample space, total number of people. All right. So total number of vaccinated people is 219. Let me see a good color for this one. 97 is going to be total number of people who caught the flu. And then here, 21 is vaccinated and flu, B and F. And so that's what we have going on here. Remember, I told you all of them would be over 490. 490 is our sample space, total number of people. And so we do 219 plus 97 minus 21. That gives us 295 over 490. And they may ask you for decimal, so always pay attention to the decimal place. They say round to 3 decimals. That must have been what they asked in the book, round to 3 decimal places. So I'll always make sure you pay attention to that. And that's your answer. All right, questions on that one? Make sure we're good. All right, questions on that rule? Problems, everybody good? Some questions may not come up until you actually try to do the stuff. So, and that's understandable. Just seeing if there's any questions on anything I've said up to this point. All right. So, I believe this is the last thing in this section. Let me take a look. Yeah, I believe so. Yep. All right, so the complement of an event. Complement of your event is the opposite of the event in question. So in other words, all elements in the sample space that are not in the event, that will be the complement. So here we see the notation for the complement is E with the C superscript like an exponent. That represents the complement of event E. So a mini example of that, if I have my sample space as 1 through 6 and my event is 1, 2, 3, then the complement of my event is going to be 4, 5, 6. So once again, your event will be one thing. The complement is everything else that is in your sample space. All right. So when you talk about calculating the probability, if you have the probability of your event, then you also can calculate the probability of your complement and vice versa. So if you see here the probability of your complement or the complement of your event, you can subtract your probability of your event from 1. Or if you have the probability of your complement, you subtract that from 1, that'll give you the probability of your event. And bottom line is that both of your probabilities, the probability of your event and the probability of your complement, are supposed to add together to give you 1. So that's why that relationship works. Very good.
I'm still getting the bottom.
In the green,
No, in the black.
right there. Okay. All right. Scroll up a little bit. Okay. So the probability of tossing a sum of 11 on the toss of 2 dice is 1 out of 18 or 1 over 18. What is the probability of not tossing the sum of 11 on the toss of 2 dice? So they give us the probability of tossing an 11. That's 1 over 18. What's the probability of not tossing an 11? So not tossing is your complement. You're talking about the opposite of your event. So that leans on this formula right here. I want to find the probability of my complement by taking the probability of my event and subtracting that from 1. So when it comes to fractions, that 1 would turn into that denominator over itself. So it turned into 18 over 18. So 18 minus 1 over 18 would be 17 over 18. All right. Any questions on that? Make sure we're okay. All right. And I scroll up. Everybody good? All right. So the next one, the probability that a person has type A blood is 34%. What is the probability that a person does not have type A blood? All right. Anybody still holding on to this red up here? All right. So it's the same type of situation. They give us the probability of having an event or an event occurring. So we're talking about the probability of having type A blood. You want to know the probability of not having type A blood. Then you will subtract that 34%. 34% as a decimal is 0.34. So you subtract that 0.34 from 1. and that'll give you 0.66. So that'll be 0.66 or 66%, depending on how they want you to answer the question. So make sure you pay attention once again to the directions in WebAssign. They want it as a percentage, you will write 66%, but they want you to keep it as a decimal. 0.66 would be the answer. Any problems, any problems? Scroll up. All right. I think this is the last one for today, unless you guys want another one. So we have a die is tossed 4 times. What is the probability that a 6 will show up at least once? All right. So first thing you want to do, like mentioned at any other time, if we're dealing with probability and you want to calculate the probability, then the first thing you want to do is establish what the sample space is. What is the total number of outcomes? All right. So we have a single die is tossed 4 times. So each one of these blocks represent a time that the die was tossed. All right. In each case, I have 6 outcomes that are possible. All right. So each one of these 6s represent the number of outcomes. You know, we have 6 numbers. So that's why I have 6 in each one of those boxes. All right. So 6 times 6 times 6 times 6 is 1,296. Remember, we talked about that when we did the fundamental counting principle. You multiply the number of outcomes in each scenario, or in each case, or in each toss in this case, and that gives us 1,296. All right. So now we want to know the probability of at least 1 being 6. Now, the probability is at least 1 being 6. Then the complement of that is a probability that none of them are 6. So sometimes when you go through trying to find the probabilities, if you find, it might be easier to find the complement than it is to find the actual probability. So what we're going to do here is look at the probability of us not getting a 6 at all. So in other words, when I go to roll these 4 die, there are 5 numbers that are not 6. So I would throw a 5 in each one of those. In other words, once again, the number of outcomes are in each box. So I'm going to explore the number that it would be, or the total number of possible outcomes if 6 is not an option. So that's why I did.
I'm sorry. Why didn't you use the number 6? Why are you using 5?
Because the probability that we want to find, it says, what is the probability that 6 will show up at least once? All right. So it's going to be easier for us to find the number of the complement, which is no sixes.
Okay.
So we're looking at what's the probability of not getting a 6 at all. So in other words, we're looking at, 1 through 5 are our only options. And so that's what we're doing right here. And so once you find a complement, then what we can do is subtract that from 1. So we're going to find the complement, which is 5 times 5 times 5. In other words, 6 is not an option. We're not using 6. What's the probability of getting 1 through 5? And that would be 5 times 5 times 5, which is 625 over that 1,296. So once again, the probability that we want is that 6 will show up at least once. The easier way to figure out that probability is to explore 6 not showing up at all. So if 6 is not there, that means we have the options of 1 through 5. And that's why we have 5s in these boxes instead of 6. That represent the options 1 through 5. So we multiply those together, got 625, and we place that over our sample space, which is 1296. I hope that's not too small. Okay, so now that we have the complement, we can subtract that from 1, which is what I did right here. And so that 1 turns into that denominator over itself. 1296 over 1296. 1296 minus 625 is 671. And, once again, either one of those answers is fine. 671 over 1296 or 0.518 as a decimal. Questions on that? Questions on what we did? All right, I believe that's the last one.
I'm still copying the answer.
Oh yeah, you're fine. You're fine. I'm not gonna change. So we are done with chapter 12. Done with chapter 12. So next class, I will not do anything new. It's one of those days we will be reviewing. You can bring your questions. No matter what chapter you pull it from, bring your questions and we can talk about it. Make sure you have clarity before we move forward. I will not be doing new material on next class. All right. Questions on anything I've said, anything I've written? Everybody good? Let's see. All right. So try this stuff out, man. See if you have any issues. If nothing else, you can look up, look at the problems in the homework and just see certain ones you want to see me to try to do. Next class, feel free to bring them to the table. And we'll go from there. Questions, concerns, comments before we close out? Anything else somebody want me to do? Some stuff, like I said, some questions may not jump up until you actually get into trying to do these homeworks. All right. So if you guys are good, I'm good. Like I said, try the stuff out, see where you're having any issues, and we're actually in a good place because, like I said, we only have 4 more sections of new content to cover. And then from there, it will be just us trying to make sure we're ready for, make sure we're closing out our assignments, actually doing them, and then getting ready for our final exam. And we'll talk about the date on that as we get closer to it. Other than that, you guys have a, yep, talk to me.
Will the final exam be on Blackboard or WebAssign?
It's going to be on WebAssign. And so what's going to happen is that I'm going to create a review. It might be already posted. I have to see if I posted it or not. The review, your final exam review, just similar to how we do in the test. That'll be very similar to your final exam. You'll be able to look at it and everything like that. So you'll know how the final exam will be shaped. And then what's going to happen is on the day of our final exam, you guys will log in. On that date, you guys will have to make sure that your cameras are available so that I can see you. It's supposed to be like simulating the actual test taking moment. Bring your ID, show it to the camera, and then I will give you the password. And then you guys will log on and just knock it out. So like the test that you guys have at your disposal now doesn't have a password. But what'll happen is you'll see the final exam as an option. If you were to click on it, it will ask you for a password, and I wouldn't give that to you until the day of. And then you guys will stay on Zoom while you take the test. And then after you're done, then you log off and you'll be finished with the class. Yep. Anything else? Anybody else? Everybody good? All right. So you guys have a good one. Be safe, and I will see you on next class.
Thank you. You too.
I have a question.
Thank you. Yep, I'm listening.
I gotta pull it up. It's on the homework. It's the lesson we went over last time.
Mm-hmm.
And you wrote the notes, and I wrote them down. So I had to look at the notes, but it wasn't any of the answers, so I was confused. So let me go to it real quick.
Mm-hmm.
Are we able to use our notes on the final exam?
Yeah, I wouldn't take that from you. You can use them. But what I would suggest is you make sure you streamline your notes so that you'll be able to, go through them, with the least amount of time possible. You don't want to be wasting time, flipping through all your notes. And
all my notes is in a notebook and
Mm-hmm.
on loose leaf paper.
Mm-hmm. Well, yeah, as long as you have a system, I think that's when your notes would be, advantageous to have.
Okay, I have it now.
All right, what are we looking at?
So it's 12.1 homework, the one we just talked about.
Mm-hmm.
It was the first one. It was like list the elements of the sample space defined by the experiment. Enter your answers as a comma separated list. And it says select an even single digit whole number. So at first my answer was like the numbers, and it was like in comma form. They said that was wrong. And then I tried other ways and it was wrong. So I'm just asking them. It's not making sense.
Okay. So let me make sure I got what you're saying. You said
12.1 and it's number 1.
Yeah, I'm trying to figure out why this thing doing this like this. Okay. So you said, you know what? I don't like this page. Hold on a second. All right. So you said a single digit even number?
It's, select an even single digit whole number.
Mm-hmm. Yep. So that should have been 2, 4, 6, 8.
That's what I put. So I was like, I must put it in the wrong way, but it said commas, so I put the commas in there.
Okay. Hold on a second.
Because I was like, I know I'm not wrong. At least that's what the note said.
All right. Let me see. So even single digit whole number. All right, so let me try it. 2, 4. Unless they wanted to use 8, 2. I mean, not 8, 0.
I guess.
Yep. You have to use 0.
Okay, then. Thank you.
Not a problem.
So irritating.
All right.
Thank you. Have a nice day.
All right, not a problem. You have a good one. All right, everybody, take care.
Have a good day.
You do the same. Thank you.